All right, here we are again. Well, under unusual circumstances. So what we need to do today is finish the sample midterm. As you know, our midterm is next Friday, March the 4th. So there's just a few more questions we have to go over. And then when that's done, we can go back to chapter 6, which we had started to do before, but it's been a while now. And so then next week on Tuesday, we'll have a normal class. We'll just go back to chapter 6. And then on Friday, we'll just do the test. Okay, so that's where we're going this week. So let me get these out. Here's the sample midterm. Now, we already did part of this. We did the fill-ins. And we did some of the problems, but we saved several probability questions for last. So let's go over them right now. And when we're done, I'll post all the answers. And then, like I said, we can pick it up again where we left off with chapter 6, which of course will not be on this midterm. It'll be on the next midterm, but not this one. All right, so let's see how we did. So number 5 is where we will pick up again today. And so in number 5, we can see that a card is chosen from a deck, and the card is replaced, and then a second card is chosen. So I've noted here that A and B are therefore independent events, because if you look at A represents the first card is a king, and B is the event that the second card is black. Because we replaced the first card before we pick the second one, that implies that A and B must be independent of each other. Okay, so in other words, whatever happens on the first card and on the second card are independent of each other. That's going to be important as we go along. That's a very important piece of information. So just as a quick reminder, in case it's been a while since you played cards, a standard deck does contain 52 cards, of which 26 are red and 26 are black. And there are 4 kings, 2 of which are red and 2 are black. Okay, the black kings are the king of spades and clubs. The red kings are the king of hearts and the king of diamonds. Also, we're assuming here, which is, I think, a good assumption, that when you pick a card from the deck, each card is equally likely to be chosen. So this is consistent with what we've been doing up to this point. Whenever we had an experiment of some kind, we were typically assuming that all the outcomes were equally likely to occur. So that will continue here. All right, if I pick a card at random, each one is equally likely to be chosen. All right, so with that being said, let's calculate these probabilities. Now, for A, for example, what is the probability that that first card is a king? Well, because all the cards are equally likely to be chosen, what we're going to basically be doing is calculating how many kings are there, and we're going to divide that by how many cards are in the deck. So with 4 kings and 52 cards in the deck, that probability is very simply 4 out of 52, or you can reduce that to 1/13. And that's really it. You don't have to write the decimal version of that if you don't want to. 4/52 or 1/13 is fine. All right, well, that was easy. Now, how about part B? The probability of getting a black card, given that there are 26 black cards in the deck, that probability is 26 out of 52, which is a half. And that's it. Now, after that, of course, we need to start using some rules. So, for example, how about the probability of A complement? So you might recall that all we have to do here is write out 1 minus the probability of A, which is equal to 1 minus 1/13, or 12/13. All right, so then for B complement, we'll have 1 minus the probability of B, and that will in turn equal 1 minus a half, or just 1/2. Now, I could have written it as 1 minus 26/52, but it will end up being the same thing anyway. So let's write that as 1/2. And again, it's just because of the mere fact that half the cards are black and half are red. Now, this is where it gets interesting. You might recall that the multiplication rule is applied to cases where we're trying to calculate the probability of an intersection. You also might remember that there's a simplified version of the multiplication rule And it is only meant to be used when A and B are independent. But that's true here, as we know, from the fact that the first card was replaced when the second one was chosen. So all of that collectively means that I am able to use the simplified multiplication rule to come up with the answer to part E. In other words, the probability of A intersect B is simply equal to the probability of A times the probability of B. Excellent. So then I just have to multiply 1/13 times a half, and I wind up with 1/26. All right, so, but if you didn't realize that these events are meant to be independent of each other, that would have been very difficult. In fact, I'm not even sure what you would have done, but the fact that they're independent makes it easy to calculate this probability. Now, that's also helpful in the next two parts because we need to know the probability of A given B, which of course is a conditional probability. And if you recall, the definition of A given B is the probability of A and B divided by the probability of B. So I looked these up from up here. Here, remember, the probability of A and B is 1/26. And the probability of B is 1/2. So the ratio of those two is equal to 1/13. Now, if you notice, what I've done here, though, is algebraically 1/26/1/2 is equivalent to 1/26 times 2/1. And that in turn gives me 2/26 or 1/13. But we actually could have done this in a slightly different way. Normally, we write out the definition of our conditional probabilities and then we solve. But here we didn't even have to bother with this. And here's why. Because remember what independence means. The probability of A given B is just equal to the probability of A. So what that means is I could have just gone up here and said, oh, wait a minute, the probability of A is 1/13. Therefore, the probability of A given B must also be 1/13. Okay, so right here you can see, because of the independence of A and B, I could have simply looked up the probability of A and come up with the same answer. Now, I wouldn't expect you to, come up with that on your own. I mean, I have to point this out to you in the beginning, but if you just went ahead and used the definition, that's fine. Either way, the final answer is 1/13. And similarly with B given A, I've got the intersection in the numerator of this ratio. And in the denominator, I have the probability of A, which means 1/26 times divided by 1/13. Algebraically, that's the equivalent of 1/26 times 13/1, or 13/26, which reduces very nicely to 1/2. But remember, and for the same reasoning, I can just say, well, the probability of B given A must equal the probability of B because of the independence of A and B. And that is simply equal to 1/2. So either way, you're going to wind up with the same result. All right, it's always nice to know when there's multiple ways of getting at a solution. In statistics, there's almost invariably multiple choices. You just pick the one that makes the most sense to you or you feel is the most straightforward. All right, now, how about H? Are A and B mutually exclusive and why or why not? And the answer here is no, because we've already proven that the probability of A intersect B is not equal to 0. And that's all you have to show to prove that they're not mutually exclusive. And in fact, if you remember, that probability was actually 1/26. Actually, let me add this in here. All right, so clearly isn't equal to 0. All right, now how about the independence? Well, we can do this again in a couple of ways. Number one, the answer is yes, because the cards were chosen with replacement. That's all it takes. But we can also use our traditional approach to demonstrating independence, which is that this condition and this condition must both be true. So you can go back and look at our results and you can see that why indeed the probability of A given B is 1/13. So is the probability of A. Down here, we note that the probability of B given A is a half, and so is the probability of B. And that means that both conditions are satisfied, and that proves that A and B are independent of each other. Okay, let me just add that here. Since both conditions are satisfied, it must be true that A and B are independent. Okay, so either way, we'll get the same result. Now, how about complements? Now, this is different because if you notice, in order for A and B to be complements, there are two requirements. It must be true that the probability of A intersect B is equal to 0, and the probability of A union B is equal to 1. Well, the first one is already false. We've already seen that. So therefore, we can stop right there and conclude that A and B are not complements. End of story. We're done. Excellent. All right. Well, that wasn't too bad. Now, how about 6? 6 is a little different because with 6, we do not know where these probabilities came from. We don't know what the sample space is. We don't know how these probabilities were generated. All we know is the numbers. And so that means for each of these, we really can only do one thing, and that's use the rules. So we basically only have one approach to calculating each of these solutions. For example, the probability of A complement, we know is equal to 1 minus the probability of A, which you can see right here is just 0.2. So we end up with 1 minus 0.2, which is 0.8. How about B complement? Well, that one is equal to the probability, 1 minus the probability of B, which means 1 minus a half, which gives us a half. Well, that's pretty straightforward. Now, how about the union? The probability of A union B, we're going to use the full version of the addition rule. We can see that A and B are not mutually exclusive, so we must use the full version of the addition rule, which means the probability of A plus the probability of B minus the probability of their intersection, which is, as you can see from the numbers, 0.2 plus 0.5 minus 0.2, and so that leaves us with 0.5. Now we have our conditional probabilities, and for these, we will have to use the definitions because we don't know for a fact whether A and B are independent. In part of problem 5, we did know that. Here we don't know that. So we'll write probability of A intersect B in the numerator, and the probability of B belongs in the denominator. And you can see by looking at the numbers up here that we'll just have 0.2 over 0.5, which reduces to 0.4. All right, now what about probability of B given A? Well, as you know, the numerator is the same. It's simply the probability of A intersect B. In the denominator, though, it's now the probability of A, and it just so happens that both of these are 0.2. It just sort of worked out that way, and so we end up with a probability of 1. All right. And then they want to know if A and B are mutually exclusive, and again, we can see that the answer is clearly no, because the probability of A intersect B is 0.2, which is clearly not 0. All right, independence. Now, again, we know the definition of independence. We know that independence requires both of these to be true. And what I did here is I looked up from up here the probability of B given A, or sorry, A given B, which is 0.4. And the probability of A is 0.2. Well, guess what? They're not equal to each other. And that's all it takes to show that they're not independent. We don't have to go any further. And that implies A and B are not independent. That's it, we're done. And then again, with the complements, we have to show two things to be true in order for A and B to be complements. What are they? Again, we have to show that the probability of A intersect B is empty, or 0 rather, and the probability of the union is equal to 1. But we can see that this is already false because the probability of A intersect B is just 0.2, which is clearly not equal to 0. And that means that A and B are not complements. Now, by the way, when you're doing this in the test, make sure you don't forget to give an explanation. Don't just say yes or no. You're also supposed to explain why. All right, so now we get to use one of our favorite tables, the joint probability table. And this involves, of course, Starbucks. It's an easy example to put together. Maybe I'll try to think of something more original for the actual test. Okay. But you can see we've got decaf and regular and 3 different flavors, French roast, Guatemala, and espresso. Most of these probabilities we can read right off the table. F, for example, part A, F and D. That is French decaf, right there, 0.18. Similarly, R and E is regular espresso, 0.10. Then for part C, R and G, regular Guatemala is 0.12. Now for French, you notice how it's just F. That means we're including decaffeinated French and regular French. The grand total of all the French roast is 0.46. For R, we're looking at all the regular flavors, and you can see they add up to 0.5. For this one, D complement, we use the complement rule, and which means 1 minus the probability of D. D over here, you can see its probability is 1/2 or 0.5. So therefore, this must be 0.5. All right, now the addition rules. Now remember here, we did say at one point that with these tables, the columns are mutually exclusive of each other. And by the way, so are the rows. So when it comes time to calculating the probability of a union from this table, we don't need to worry about the intersection between F and G. It's just empty. The probability of F and G is 0. So we can use the simplified version of the addition rule. And that means that we can simply add the probability of F, or 0.46, with G, which is 0.22, and the grand total is 0.68. And then we're done. That's it. Similarly, for G or E, or G union E, this is Guatemala or espresso. We'll add up the total for G and for E, and we end up with 0.22 plus 0.32, which is 0.54. All right, and then finally, D given F, these last 3 are conditional probabilities. So I've written out the definitions. For this one, we have the probability D and F over the probability of F, or 0.18, which we've already seen, over the probability of F, which actually we've already seen this one too, 0.46, and that ratio equals 0.3913. Now, how about this one? R given E, regular given espresso. So we have the intersection between them here, R and E, regular espresso, which is 0.10. We've already calculated that one. E by itself, we look at the total of this column, and we see that that's 0.32. So that ratio is 0.3125. That's our answer. Very good. Now, G given R, Guatemala and regular. So in the numerator of this expression, we have the probability of G and R, or oh, there it is. We already have it. And of course, don't forget, just as a side note, the order in which you write an intersection like this does not matter. So therefore, here I'm writing G intersect R. Up here, I wrote it as R intersect G. It's the same thing. In both cases, it's 0.12. All right, so don't forget about that. And the same thing is true, by the way, for unions. For GUE here, G union E, it's the same thing as E union G. I just want to remind you. Anyway, so that means we have 0.12 in the numerator. R by itself, as we've already seen, is 0.5. That ratio is 0.24. And that's it. That's all we have to do. So this type of problem is very, very straightforward. I think we covered everything here. Yep. All right. So we saved the best for last. Bayes theorem. Now, how do you know that this question 8 is a Bayes theorem question? Well, there's a tip off here. We have a lot of probabilities given to us. So let's look at this thing for a second. If the economy recovers next year, the probability that the price of stock X will rise is 40%. Now that is clearly a conditional probability because two things are involved: the stock going up and the economy being in recession, or sorry, in this case, recovery. The next statement, if the economy remains in recession, the probability drops to 10%. And of course, that means the probability of the stock price rising. Once again, it's a conditional probability because we have two pieces of information in there. The next sentence gives us two unconditional probabilities: the probability of recovery and the probability of a recession. Those are unconditional. So if you recall the way these problems are structured, we have a sample space which is broken up into a partition, and the events that form that partition in this case are the recovery and the recession. How do you know that? Because they're given to us as unconditional probabilities. And furthermore, these two probabilities have to add up to 100%. So I wrote them over here. I'm going to assign A1 to be the recovery and A2 to be the recession. And as I mentioned, they do add up to 1, which is exactly what we need. That means that stock X rising or not rising depends on the state of the economy. We call that event B, and event B depends on what state of the economy we're in. In other words, the stock price rising depends on the state of the economy. So the probabilities that we were given about this, let's read them and make sure we understand. So it says here, if the economy recovers, all right, so assuming that we know that A1 is true, the probability that the price of the stock goes up is 40%. So this in symbols means the probability of B given A1 is 0.40. Okay, and here it is right here. The probability of B given A1, the probability of the stock price rising during a recovery is 40%. Then we notice that here, if the economy remains in recession, the probability will drop to 10%. So we can think of this as the probability of the stock going up during a recession is only 10%. So this is B given A2. Now, I do want to point out, if you're not sure that you got these right, that the unconditional probabilities have to add up to 1. The conditional probabilities do not. They usually don't. So if your A's, if the A's that you chose add up to 1 in probability, you've probably done this correctly. If you get them backwards, what will happen is you'll come down to this formula and you'll realize you don't have enough information to solve for it. So you would have to go back and rearrange the definitions. Okay, once that's done, then we want to ask ourselves, what exactly are we supposed to know or figure out? If the price of X rises next year, so that's known information, what is the probability that the economy is in recovery? What that is equivalent to is saying, what is the probability of A1, a recovery, given that we observe that the stock price goes up? So that is the question that we're being asked. The probability of A1 given B. And that's where the Bayes theorem formula comes in. Okay, so let's look at this thing and try to figure out how to turn this formula into this one down here. So in the numerator, we'll have A1. Well, this one, we're being asked about A1, not A2, A1. So we only will have A1 in the numerator. So we write that as the probability of B given A1 times the probability of A1. In the denominator, we take into account all of the A's in our partition. So in other words, we have the same term again, then we have to do it all over again for A2. Once this has been written out, then you'll just have to plug in the numbers and do the math. So that's the easy part. The tricky part is setting up this, okay, and interpreting the question. Once that's done, it's just a question of substituting in the numbers and then doing the algebra. And in this case, you can see that you've got 0.12 divided by 0.19, and that ratio is equal to approximately 0.6316 or 63.16%. And they're all the same. The only thing that might change is that in some problems, there might be 3 A's, A1, A2, and A3. There won't be more than that. Okay, I can tell you right now, on the test, there's either 2 or 3 elements in the partition, no more. All right, so we're actually done with this sample midterm. I'm going to post these answers. Now, we started them the other day, and now we have these. I have a document where all the answers are formally typed up, so I'll be posting that and this, so you can go through and double check what we've done. And if you have any more questions, you can still ask them next Tuesday, of course. But if not, we'll just continue with chapter 6. So let me save this and put it away. And then we'll go back and revisit chapter 6. We did start it, but we didn't get that far. So we also don't want to waste any time. So we're going to go back here and revisit chapter 6. So you might remember that this chapter is all about what we call discrete probability distributions. We're going to talk about 2 very important concepts, the random variable and the probability distribution. So using the case that we had earlier where we roll a die twice, first thing we want to notice is that the random variable does exactly one thing, and that's assign numerical values to the outcomes of an experiment. So here's the case that we've been looking at. We roll the die twice, and we only focus our attention on evens and odds. X will be defined as how many even numbers turn up when we conduct this experiment. Okay, so it's a very simple case. X can only assume values 0, 1, and 2 because we're only rolling the die twice. Let's look at this chart now. So for example, if you get EE when you roll the die twice, X will be assigning a value of 2 to that outcome. If we get either EO or OE, then X will be 1 because there's only one even number in both of these cases. And then finally with OO, X is 0 because there are no even numbers. So this is what X is doing. It's just taking all the possible outcomes and turning them into numbers. Okay. The reason why we're doing that is so that we can calculate probabilities with formulas rather than counting out all the possible outcomes of our experiment, which is fine when you only roll the die twice. But if I roll the die 10 times, wow, that sample space will contain 1,024 possible outcomes. And I don't want to then calculate probabilities like 6 heads or 6 evens or 5 odds or whatever. It's going to get very clumsy and very quickly. So that's why we would prefer to use numbers. And by having numbers, we can calculate an algebraic formula that will let us calculate any probability that we need. So that's why this is so important. Now, here's the calculations of the probabilities. Again, remember, we're assuming that these outcomes are all equally likely. So therefore, the chances of getting a 2 on that, or the chances of X equaling 2, are only going to be 1 out of 4. Because there's 4 outcomes, only one of them is X equal to 2. Therefore, it gets a probability of 1 out of 4. 1 is different though. There's 2 ways this can happen. out of 4 total possibilities, which implies that X will have a probability of 2 out of 4, or a half, of course. And then for 2, well, guess what? There's only one way this can happen. Therefore, its probability is also a quarter. So we can gather these together into a nice little table. And you can see, here's all my X's, here's all their probabilities. This is what we mean by a probability distribution. It's a table. That's all it is. Now, if we chose to do so, we could probably dream up a formula that corresponds to this table. We're not going to do that here. It's not really worth our trouble because it's so simple. But most of the time, we're going to try to have a formula rather than a table. It's just easier. And of course, X is the random variable that we defined earlier as the number of evens that turn up. A couple of important things to note here about this probability distribution. Number one, the individual probabilities are non-negative. We can't have negative probabilities because that would violate the axioms of probability. We cannot violate those axioms. Okay, the entire system of logic that we're developing here is based on those axioms. We can't make any exceptions, all right? All probability distributions must have probabilities that are non-negative. And furthermore, the sum of these probabilities has to be exactly 1. That's all we have to choose from. Anything else is not considered to be a probability distribution. With those being established, then we can use these distributions to come up with important results. Also, because X only has a finite number of possible values, it is classified as discrete. Okay, so when we spell the word like this means a finite number of possible values. The opposite of that, which we'll see in the next chapter, is continuous. This requires X to have an infinite number of possibilities, which we then obviously can't describe with a table. For that, we must have a formula. Okay. And also, by the way, we'll be using calculators for these probabilities. In this chapter, we can do them manually. But once we get into chapter 7 with continuous random variables, we have to do everything with a calculator. Now, and to summarize, this is the probability distribution that we created. No problems there. We already know that it's valid because the individual probabilities are non-negative. The sum is 1. Right there, you can see the first two axioms of probability are being obeyed. And you might recall that with samples and populations, we often used summary measures to describe their key properties. We learned 3 of them, as a matter of fact: measures of central tendency, measures of dispersion, and of course, measures of association. We're going to do something very similar here. Random variables are important, but often we can summarize their key properties with its own unique set of measures. These measures have a slightly different name. Instead of calling them measures, we're going to call them moments. All right. So in statistics, we see a lot of cases where similar concepts have different names. The reason for doing this is so that we know when we say the word moment, we know that we're talking about a random variable, as opposed to a sample or a population. There are 3 of them, though. We're only going to look at 3. All right, here we had a lot of them. There were tons of them. And these all apply to random variables too, but we're only interested in 3 of them right now. Expected value, which is the same thing as mean, variance, and standard deviation. The others, well, you will run into them in a more advanced class if you ever take one, but not here. Something to look forward to, right? All right. So anyway, how were these defined? Well, unlike with samples and populations, these formulas involve probabilities. Of course they do, because we're talking about random variables. So in order to calculate the expected value of X, or the average or mean value of X, this is the formula that we'll be using. Now, what do you notice here? Well, we're going to go through all the different possible x's. Now, by the way, here's something we have to watch out for. The capital X is the random variable. The lowercase x is a single possible value of capital X. Okay, so in other words, we have to be careful about this. This is a single value of the random variable, one of the possibilities. This is its probability. This one, you can think of it as the probability of that xi. By multiplying these out and adding them up, we end up with our expected value of x, which is essentially the same thing as an average or a mean. So we're going to do that right now with our die rolling experiment. We're going to see what the expected number of evens is. Okay. So I reproduced the chart up here. If you think of this 0 as the first possible value of x, think of this as x1, x2. Let me draw that a little better. x1, I'm trying to make it clear that this is a lowercase x. And then these would be the probabilities. And so what I'm going to basically do is just multiply them all together and add them up. Okay, so I've written it out here so you can see what I've done. I go through all the x's, and for each one I multiply by the probability. And when I'm done adding them up, you can see the final result is just 1. Okay, 1. So think of this as if I roll the die twice, on average, I'll get a single even number. Now, of course, sometimes I'll get none, sometimes I'll get 2, sometimes I'll get 1. On average, I should get 1. The 0s and 2s should balance each other off. So on average, I'm getting a 1, which is what you would expect. But what about the variance and the standard deviation? Those are a little bit more difficult to interpret. How are they calculated? All right, well, let's take a look. The formula looks a little scary, but it's actually no different than what we did with variances and standard variances for populations and samples, except that we have probabilities here, which we did not have with our samples and populations. You're basically doing a 3-step process. You take each x, each outcome, subtract the expected value, square the difference, weight this by its probability, and then finally at the end you add them up. So it's a little bit complicated, but we'll see in the next slide, it's not really that bad. And one more thing too, if you notice, the sigma squared can either be used to represent a population variance, but now we're seeing it being used as the variance of a random variable. Well, that's confusing, isn't it? No, it shouldn't be, because it should be clear from the context that you're using, whatever problem you're working on, which one it is. Okay, so that's why statisticians did not set up separate variables for random variables. I guess they figured, well, it should be obvious what you're doing here. We'll continue to call variance sigma squared then. I don't know if it's the right decision, but this is how it was done. So anyway, so let's see how that would work in this case. So I wrote on the top what each variable represents. And if you notice, in each case, I'm subtracting 1 because that's the expected value. I'm applying this to every one of the 3 x's. I square the differences, weight each one by its own probability, add them up, and it turns out to be a half. Okay. Not that bad. No, it could have been a lot worse, let me tell you. So you got a half as your variance. Now, like with samples and populations, the standard deviation is simply the square root of the variance. And that hasn't changed. It's the same here. So we'll go on now to the standard deviation. And we're going to define that as sigma, just like with the population. And you can see that the standard deviation is the square root of the variance, or in this case, the square root of a half, which is approximately 0.7071. Okay, and that's it. That's all you have to do. All right. Now, of course, you can see that would be very complicated if we have a large number of different possible values for x. Here, we're looking at a simple case, but the principle is the same, no matter how large, how many x's we have. All right, now, the title of this chapter is Discrete Probability Distributions. What we're going to do now is introduce two very widely used discrete probability distributions. There are actually a lot of them to choose from. They all have different purposes. Okay, it's like having a gigantic toolbox, and you use the tools depending on what job you're doing. All right, like you use a wrench for some purposes, you use a saw for other purposes. And it's the same thing here. You've got all these distributions to choose from. Each one of these is an attempt to explain some type of behavior in the real world. But some are more popular than others. All right. So the two that I'm about to show you are very commonly used in finance and in economics and other business disciplines. And here's some good news for you. Although I'm going to show you how to calculate these correctly, it turns out there are shortcuts hiding in our calculators that we can use later on. Once you understand how this works, then I'm going to show you some shortcuts. So if these formulas seem terribly scary, well, don't worry, down the road, I'll show you some shortcuts. So here are the two that I want us to look at. The first one is called binomial. And I circled that prefix bi to remind you that it simply stands for two. Any English word that starts with bi, all right, I shouldn't say that, not every English word. There's always exceptions, but for the most part, bi is used to introduce a word, and it means two. The classic example is bicycle. What does that even mean? Two wheels, okay? So binomial means two, but we don't know just yet what that actually refers to. The second one is called Poisson, and that one is named after its inventor. So therefore, the name doesn't tell you anything, all right? But at least with binomial, you get a feel for what this is going to be all about because of that prefix bi. All right, now, these are special cases. In order to use these probability distributions, we must make sure that certain conditions are met. Otherwise, our results will not be very useful. So in other words, we can't just blindly apply these whenever we feel like it. They're meant for specific situations. And if those conditions are met, then we should get some highly accurate results. If not, the results will not be very useful. So we'll start by examining the binomial distribution. And it turns out that we can use this if our experiment satisfies three important properties. All right, so in other words, we are assuming that there's some kind of a process taking place where there's several trials, like for example, rolling the die twice is an example of this. We have two trials of an experiment. Or I could, for example, flip a coin 8 times. Then I would have 8 trials of this experiment. Well, here, in order to use the binomial distribution, it must be the case that number one, the trials are independent of the other trials. In the same way that we had independence in the previous chapter, it simply means that the trials do not influence each other. Like when you flip a coin, I mean, if I flip the coin and it comes up heads, that does not affect the likelihood of getting ahead on the next flip. The coin flips do not influence each other. So we could think of those as independent trials of an experiment where I'm flipping a coin, right? So it's important that these trials be independent of each other. And then specifically, we are allowing only for 2 possible outcomes of each trial. We will randomly assign them the names success and failure. For example, if I'm flipping a coin and I'm mainly interested in how many heads turn up, I could let head be success and tails be failure. It doesn't matter which is which, but this is how it's done. Success and failure. Yes or no, that kind of thing. It's either something happens or it doesn't. And then the third requirement is that the probability of getting a success on a given trial, which in this book is designated with the letter pi, is a constant from one trial to the next. In other words, it never changes. And again, you can think of this in terms of a coin flipping experiment. Does the probability of getting ahead ever change? No, it's always a half every time. So if all 3 of these conditions are met, then the experiment that we're carrying out is formally known as a binomial experiment. And if that's the case, we can define a very special random variable called x, which is meant to represent the number of successes that occur on n trials of the experiment. And then we say that x is binomial, or it follows the binomial distribution, or you could equivalently say it is binomially distributed. Okay, and that means we now have the right to use a special formula to calculate probabilities for x, which will save us a lot of time. I mean, that's the whole motivation here. We want to save time. Well, it turns out that there's in principle an infinite number of different possible binomial distributions. What separates one from another is the value of n, the number of trials, and pi, the probability of success. Don't worry, we'll get more deeply into that later on, but right now we want to focus our attention on understanding how to calculate binomial probabilities. Now, the formula that we will be using is not excessively complicated, but there are some components of it that you may not be familiar with. So what we're going to do next is look at the formula, and then we're going to pick it apart and see what it means. And along the way, we're going to introduce some pretty interesting new ideas. What do I mean by that? Let's take a look. So when you see this formula, you'll realize right away there's one term that you may not recognize. Although it's possible you've seen this before, there's a very real chance that you haven't. So this is what it looks like. Now, I think it's pretty clear. What is this thing with the gigantic parentheses around it? That's what we want to analyze. But just keep in mind, in this formula, we see n, which is the number of trials, x, the number of successes on those trials, and pi, the probability of success. So you can see what's going on the right-hand side here is very simple. I mean, it's pretty clear what you're doing here, but this is something that might be brand new to you. We're going to take a step back and explain what this represents. Okay, well, first things first, this is defined in terms of a mathematical operator which you may or may not have seen before. Okay, now if you notice, I've got all these exclamation points all over the place. In math, this is known as the factorial operator. So in other words, if you have n with a factorial symbol after it, in English, we call that n factorial, or for x, the same thing, x factorial. So the question becomes, what does that represent? What is that telling us to do? And by the way, you'll be relieved to hear that this is available on your calculator. I'll show it to you in a few minutes. So it's a very interesting idea. The way it works is this. First of all, it's only defined for the non-negative integers. The first two are very simple. Both 0 and 1 factorial equal 1. But then it gets interesting. 2 factorial is 2 times 1, or 2. 3 factorial is 3 times 2 times 1, or 6. 4 factorial is 4 times 3 times 2 times 1, or 24. And I wrote in another one, I think it's pretty clear that 5 factorial would just be 5 times 4 times 3 times 2 times 1, or 120. So the question becomes, what exactly is this telling me? Well, here's a nice, interesting application of this. Imagine yourself moving into school in September. All right, you're coming back after the long summer. You're bringing all your stuff with you. And of course, you have plenty of posters to hang up on those bare walls. And here's the 3 that you brought with you. You've got a poster about the Yankees. You've got a poster of Salvador Dali's paintings. And of course, you have a poster that celebrates statistics. Here's the thing, though. You've got exactly enough space in the wall to hang 3 posters from left to right, let's say. That's all the space you have. Here's the question. How many ways can these posters be hung from left to right? All right, well, what I've done here for you is I've written out a list. Let's take a look. So, of course, you can see that I've abbreviated the names. Y for Yankees, D for Dali, S for statistics. And you can see there's 6 different ways of hanging the posters from left to right. That's it. That's all we have. Okay. Then you would figure this out for yourself. If you had them there in front of you, you could try different ways of hanging them. And you discover pretty quickly that you've got 6 possibilities here. Each of these choices is known as an arrangement. So mathematically, an arrangement means that you're taking a group of objects and changing their order. And that's all you're doing. You're changing the order. You're still using all 3 of them here, but there's 6 different ways I can change the order and hang those posters. Which means when I have 3 posters, there are 6 different arrangements that I can create. And of course, it doesn't have to be posters. It could be anything. It could be books on a shelf, for example. It could be cars in a garage. As long as we're changing the order, each way I can rearrange the ordering is called an arrangement. Now, if you notice here, I was able to find out how many arrangements I have available to me by simply writing them all out. If I had more posters and more space, this eventually would have become very difficult. In fact, it turns out that if I had a 4th poster and enough room for all 4 of them, the number of choices would have jumped up from 6 to 24. Wow, that's a lot of choices. So writing them all out would have been a very time-consuming process. So I don't want to do that, do I? No, but it isn't necessary. Here's why. Because it turns out that n factorial tells me how many arrangements I can create from n objects. Okay, so if I have 3 posters, n is 3, and since 3 factorial is 6, that means there are 6 ways of hanging my posters. That's all I have to do. So instead of writing them all down, I can just say, this is 3 factorial. Easy. It's equal to 6 because 3 factorial is equal to 3 times 2 times 1, which is equal to 6. Oh, wow. So that's what that means. Now, suppose you say to yourself, you know what, that's fine for small numbers. What if I have 10 posters? That could get really big in a hurry. Well, luckily, it turns out that I can do this directly on the calculator. Here's what I want you to do. If you have the calculator right there, let's implement 3 factorial. What you have to do is type 3, and then it turns out that there's a math button up there, which you may not have noticed before. It's in the extreme upper left-hand corner. So start with a 3 and hit math, and then you'll see a bunch of menus up there. The one you want is on the far right. It's called PRB for probability. Choose that, and then scroll down to number 4, which is our factorial operator. And then all you have to do is hit enter. And it comes back with a 6. Wow, that was easy. So I'll just label these. So imagine you had chosen, what if you had a gigantic room and you have 10 posters? So for 10, you'll see in a minute why this is better to use the calculator than doing it by hand. So I'll steal this example. So for 10 posters, the number of arrangements is, so you just change this 10 to this 3 to a 10, and you're not going to get 6, that's for sure. Let's see how gigantic that is. I think you'll be surprised when you see this 10, math, probability, 4 for factorial, enter. Ooh, look at the size of that number. Look at all those zeros. 3,628,800. Can you imagine how long it would have taken for you to sit there and write out all the different ways of arranging those posters? You would have been doing this well into next month. Okay, so that's why it's so helpful that this is available on your calculator. Now, as it turns out, though, the factorial operator itself is important, but this term that I showed you earlier has another very important significance. In other words, the entire term, not just the individual factorials, but the entire term has a very important significance. But because it's a fairly complicated concept, and because it's Friday, this is where I stopped in the other class, and I think we'll do the same thing here. What we'll do is we'll take a look at this. We're going to learn about some new ideas. And what's different here is that instead of just arranging objects, we're going to be selecting objects from a larger collection and then changing the ordering. And so we're going to build up to something more complicated. And when we're done with all that, we'll be able to finally go ahead and use the binomial formula. So I think we've gotten quite a bit done today, so we can stop right here. And when we pick it up again on Tuesday, we'll see exactly what this term is telling us. Okay, so something to look forward to. But in the meantime, if you have any more questions about the exam or the sample midterm, we can go over those on Tuesday. But for the most part, we're going to focus on this. All right, and then of course on Friday the 4th, we're going to do the test. Okay, so I hope you're all ready. And so if there's no last minute questions, I think we can stop right here. And I'll see you all next Tuesday. All right.